This is a presentation on kinematic camber gain and bump steer by Nate Evans, Jade Kowalis, and Daniel Turley in association with BYU Racing. Camber refers to the tilt of the top of a vehicle's tire toward or away from the center of the car when viewed from the front. When a vehicle turns, the body of the vehicle has a tendency to roll to the outside of the turn. The vehicle leans slightly, and the suspension of the outside wheel of the turning radius must compress. When racing, it is desirable to have a slight camber gain to increase turning stability by maintaining a more constant amount of tire and ground contact during the turn. Here you can see our two-dimensional prototype traveling through its motion. The triangle represents the steering knuckle that is rigidly attached to the wheel and tire assembly. Notice that the top of the triangle tilts toward the left, where the center of the car would be, as the suspension arms travel upward. Although the suspension on this vehicle is three-dimensional and includes many additional angles, the same principles for camber gain still apply. As the wheel is lifted up, the top of the wheel gradually tilts toward the center of the car. We chose to use three-position complex number synthesis for our prototype. The three positions were chosen to be static equilibrium, half compressed, and fully compressed. Each suspension position represents a critical orientation of the steering knuckle. The first dyad represents the lower arm of the suspension mechanism, with the coupler point as the center of gravity of the wheel. The second dyad represents the upper half of the suspension mechanism. These four vector equations define the first and second dyads between their respective positions, 1 to 2 and 1 to 3. These are the equations written in complex exponential form. Writing the equations in this form helps us create the right formulas in the next slides. Now the equations are written in complex form, so each equation can be split into real and imaginary parts. Completing this step allows us to create enough equations to solve for all of the unknown variables. The unknowns in the first dyad are w, theta, p21x, and p31x, while the unknowns in the second dyad are u, sigma, gamma 2, and gamma 3. All other variables were either known or were free choices. Here are the real equations that can now be solved using a nonlinear equation solver. Here are the imaginary equations which will be solved in a similar manner. After all of these equations were solved for the desired unknowns, the mechanism was constructed and tested to analyze and verify its performance. The camber angle was measured at the three predefined positions, and it changed within a very narrow tolerance window of how it was designed. All three positions are shown here. Bump steer refers to a design flaw that steers the wheels due to suspension travel and not from actuation in the steering wheel. Although it is impossible to eliminate bump steer completely, its minimization is desired because it can lead to unwanted turning when the vehicle travels over terrain. This portion of the synthesis will show how to place the tie rods to minimize bump steer. First, the front view of the suspension is sketched, and lines are drawn to find the location of the instant center between the steering knuckle and the vehicle chassis. The tie rod length is determined as shown. A line projected through the tie rod should intersect the instant center of the coupler and ground links. Here is the suspension in the second position. Notice that the line through the tie rod points very near to the new instant center between the steering knuckle and the vehicle body. Here is a zoomed-in view. Because the tie rod no longer points exactly at the same instant center, there will be a small amount of bump steer. Here is the top of the suspension travel. Notice that the tie rod line has moved farther from the instant center than it was before. This will cause more bump steer. Our prototype shows how bump steer works. Because the tie rod, which is the middle link, is in the same plane as the upper and lower links, the mechanism's travel is limited. One of the links has to change length to achieve full range of travel. From this side view, it is evident that the mechanism is overconstrained. Therefore, one link buckles when the coupler is pushed beyond a certain point. In an actual steering system, the tie rod would steer the wheels rather than buckle. Here is a video of a car that was designed to have minimal bump steer. This front wheel moves very little as it travels up and down relative to the chassis. Here is the other front wheel. There is slightly more bump steer on the outside when the wheels are turned as shown. Here is a video of a car that was not designed to have minimal bump steer. This is the other front wheel of the same car. When not accounted for, bump steer can seriously affect vehicle performance. So there you have it. Designing an effective suspension system requires careful kinematic analysis and synthesis.